In this lesson, we're going to discuss factoring polynomials. There are a lot of different strategies to use when factoring polynomials, and it all depends on what the polynomial looks like, how many terms it has, what the coefficients are made of. But first, we need to define all of these terms. So we will start out with, what is a factor? Well, a factor is a number or expression that divides another evenly. So one example, I'll write it up top here. Here I have a polynomial, 8x squared plus 6x plus 4. And I'm actually going to change one of these signs. Let's make it 8x squared minus 6x plus 4. This is an example of a polynomial. It's a pretty simple one because all of my coefficients are integers. The coefficients are the numbers in the front. The variables are the x's in this case, but polynomials could have more than one variable. We could have x, y, and z. We could have other variables, any letter to represent an unknown. But with a polynomial, the exponents on the variables must be whole numbers, 0, 1, 2, 3, etc. The coefficients can be any real number. So instead of 8, we could have square root of 2. Instead of negative 6, we could have negative 3 pi. Instead of 4, we could have 17.359. So we could have any numbers for coefficients, but the exponents on the variables must be whole number exponents. And we're not dividing by variables or variables being under square roots. Those are not allowed for a polynomial. Another definition that we need is a term. Terms are the part of polynomials that are separated by addition and subtraction. So we have 3 terms in this polynomial. What does it mean to factor? So if we use factor as a verb, it means to break down a number or expression into its factors. One example, back to our polynomial up here, and we will talk more about this later on. Notice that 8 and 6 and 4 are all even. Even numbers are all divisible by 2. So we could take a 2 out of each one of these terms, and then grouping them together, we can factor out that 2. And again, we'll talk more about what this strategy is. This is actually the distributive property, but in reverse. Instead of distributing the 2, we're pulling the 2 out. So that's one example of factoring a polynomial. And again, we're going to explore this a lot more later on. Let's start with just numbers. Find the prime factorization of the following. We want to find the prime factorization of 48. So here's another definition for you. This idea of prime factorization, it means we're going to take that 48 and we're going to break it down so far that all we have that equals 48 will be prime numbers multiplied together. So to give you a quick example for prime factorization, 8 is 2 times 4, but 4 is not prime. If we break 4 down even more into 2 times 2, this would be the prime factorization of 8. 2 times 2 times 2, or 2 to the third. That's what we want to do with these two problems with 48 and 60. So this idea of a tree, we're going to think of 2 numbers that multiply to be 48, any 2 numbers, it doesn't matter what they are. Your tree may be different from my tree. There are lots of possible answers for many numbers. But the end result, the leaves of the tree, if you will, should all be the same. So if I'm thinking about multiplication tables, or if we use our calculators, if the numbers are too big and we can't remember that easily, we can break 48 into multiplying 2 numbers together. I think of 6 times 8. 6 times 8 is 48. I see that neither of those are prime, so I'm going to break them down further. 6 is 2 times 3. 8 is 2 times 4. And when I get to a prime number, I'm going to circle it, because that means my tree is done on that branch. It grew a leaf, if you will. The prime numbers are the leaves of the tree. So 2, 3, and 2 are the leaves. It means I'm done. 4, however, can go further. 4 is 2 times 2, and those are prime. So we end up with 48, 2 times 2 times 2 times 2 times 3, or 2 to the 4th times 3, if we want to use exponential notation. For 48, you could also think of 12 times 4, or 2 times 24 as that first step. Any of those would be fine. Or 3 times 16 would also work. Lots of different options for finding two numbers that multiply to be 48. So if your tree starts with any of those, it's perfectly fine. At this time, pause the video and see if you can try 60 on your own. I'll have the answer when you resume, so make sure you hit that pause. Try it on your own, see if you can come up with the prime factorization of 60 using this idea of a prime factorization tree. For 60, anytime it ends in a 0, I automatically think of my tens multiplication, so I'm going to do 6 times 10. You could do 4 times 15, or 3 times 20, or 5 times 12. Any of those would work. 6 is 2 times 3. 10 is 2 times 5. And so 60, 2 times 2 times 3 times 5, 2 squared times 3 times 5 would be our prime factorization for 60. That's the first step for factoring. We want to be able to take the coefficients and break them down so that we can recognize common factors. So looking at 48 and 60, do they have factors in common? Do they have common prime factors? Well, I see that 48 and 60 both have 1, 2 2's, and I also see that they both have a 3. So for 48 and 60, 2 times 2 times 3 is what they have in common. If I multiply those together, I get 12. We say that 12 is the greatest common factor of 48 and 60. Now, this idea of greatest common factor, it can be a little confusing. The word greatest you automatically think of as big, but the greatest common factor is the largest number that divides both of those numbers. When we're talking about numbers dividing other numbers, we have to have smaller numbers. So just be careful with this idea of greatest common factor. We're looking for one number that divides both of the numbers given, 48 and 60. And 12 is the largest of the numbers that divide both of them. Notice 4 divides both, 3 divides both, 6 divides both. One of our goals in factoring polynomials is to find the greatest common factor of all the terms. Let's start out with just a single term. We're going to find all the factorizations of 6x cubed. So all the factorizations of 6x cubed. Pause the video, see if you can do this on your own. The order does not matter, so 2 times 3 and 3 times 2 are the same factoring, but there will be 8 different distinct factorings of 6x cubed. So see if you can come up with all 8 of them. So we could start out with 6 and x cubed. We could break the x into x and x squared, and we can break the x squared even further. We could look at 2 times 3 instead of 6, and then we can play the same game with the x's. And that gets us 6 factorings. So then to get the other 2, And actually, I take that back. There are more than 8 distinct factorings, and I'll show you why in just a minute. We can look at 2x and 3x squared, or 2x squared and 3x. And I forgot, I could have done 6x cubed and 1. I could have done 6x and x squared, and I could have done 6x squared and x. So that would give me 11 different factorings. But if you came up with the first 8, good job. Or if you came up with any of them, congratulations. And then take notice, the greatest common factor, or GCF, is the largest factor that every single term has in common. And finding the greatest common factor of all of the terms is actually the very first step in factoring polynomials. So let's take some time and practice more. I'll do a few. We'll do 7 together, and 9, 12, and I'll leave the other 4 for you to try. And if you want to find the solutions, go check out the OneNote link, and you'll be able to see all of the solutions worked out. So let's take number 7. One way we can find the greatest common factor for all of these terms is to write out the prime factorization. And even though we have prime factorizations of variables in this case, it just means we break apart the variables. So xy is x times y. X squared y squared we can write as x times y times y. And then x cubed would be x times x times x. And then we look at, what do they have in common? All of them have an x. The first 2 have a y, but the third one doesn't. The second and third both have an x, but the first one doesn't have an extra x. So we don't want to count any more x's or y's, which means our greatest common factor for number 7 is just x. In number 9, we can play the same game. Negative 20x squared. Let's pull the negative out as a -1. 20 is 2 times 10. 10 is 2 times 5. And then we have x squared. 12x. 4 times 3. But 4 is 2 times 2. And then x. And 40x cubed. 40 is 4 times 10. So 2 times 2 is 4. 2 times 5 is 10, and then x cubed. And now we look for common factors. So I have a 2 in all of them. I have a second 2 in all of them. 5 in 2 of them, but not in the middle. 3 in the middle, but not in the others. And then x in all of them. And I only have 1 x in all of them because of that 12x. So my greatest common factor, take one row, 2 times x, which would be 4x for my greatest common factor. Now let's look at number 12. Number 12 is very different because we have x minus 2. We have subtraction here. Notice that 11 and 13 are very similar. They have addition. So we have terms. Remember, we're factoring, so we have to make sure we find factors. Now, I know I didn't say this earlier, but factors are separated by multiplication, not addition and subtraction. So even though both of them have an x and both of them have a 2, I cannot look at them separate like that. I have to look at them together. X minus 2 is one unit, one factor. So I'm going to put a parenthesis right around that second x minus 2. Notice here, both of them have x minus 2. If I'm talking about factors, I would have x times x minus 2 in the first one, In the second one, I could look at it as 1 times x minus 2, but I don't get to separate x and the minus 2. They have to stay the same. And so for that, now looking at what do they have in common as far as factors go, both of them have x minus 2. So my greatest common factor is x minus 2. Try the other ones on your own. Check your work against my OneNote. See if you can get the same answers that I can. If you can't, make note of your mistake. Don't try to erase it. Make note of it, come back to it, correct your mistakes so that you can keep track of what did you do, what did you try, and why it didn't work. And we'll resume this lesson talking about the distributive property next.